So the title of my presentation today is Redesigning, Repurposing, and Revitalizing Civil Structures. So we heard from Mark and Chris of how they made use of existing building structures to repurpose for the current use and future uses. And this presentation is mainly focusing on how to make use of historic civil structures. Before I get into the presentation, I thought I'll give a bit of an introduction of myself and what I have been doing in the last 30 odd years. And then we look at the reasons for why we need to repurpose, revitalize, or redesign the existing civil structures and some of the significant problems through real life examples. And we will focus on key challenges and lessons learned. I just thought I'll share with you the journey I have taken in the past 3 decades. So I originally started my education in Sri Lanka and then moved to the UK to do my postgraduate education and spent about 8 years doing studies and work before moving to New Zealand. So the last 25 years were mainly spent in New Zealand, few years in Australia and Japan. Although I worked in building structures, most of my experience in consulting engineering is mainly on civil structures. And in New Zealand, I focused on land transport infrastructure projects, both new builds and repurposing existing structures. And one thing we specialize here very much is how to look after the existing structures as well. As you know, we are sitting on the ring of fire, so time to time we experience major earthquakes. And so seismic engineers, a critical part. I'm not going to share much on seismic retrofit, but I thought it's good to mention. And as we heard from other speakers, most of my current life is on looking at how to get more from less and how to make use of existing structures without building new ones. So we're looking for value for money. So it's interesting to look at why we need to repurpose these structures, because there itself lies the important message that we don't need to build new stuff all the time. And currently we know the climate change and environmental situation and decarbonization, everything points to us that the more we reuse, the better life for us and the future generations. So some of the reasons in the past being that when we designed these structures 100, 200 years ago, they weren't designed for durability in mind. So often we need to intervene to look after the structures. And significant increase in demands, live load demands and code changes and various other demands make them need to be upgraded. So that's another reason for revitalizing. And as you would see in one of the examples, they become slightly redundant or not much further use can be gained. So then we need to look at, should we retain or dispose them? And often when they reach the end of the life, it's also important to look at what to do. And now it's even more important, look at how to demolish or reuse the structures when they reach the end of the life. So I thought it's good to show some real examples that I worked on in the past 20 years in New Zealand. And these are both road bridges and also one rail bridge where we done significant intervention to retain or revitalize the structure. So the first one is Coronation Bridge in Auckland, in New Zealand. And this was done in early 2000s and when I was working at Baker. As you would see, it's a concrete arch bridge. And the reason for its name, it was the first crossing was built in 1911 when King George V was crowned. So that's how the name came about, and it was a timber crossing. And in sometime in 1940s, I think it's 1947, that bridge became redundant because it had to be replaced by the current bridge when they built the Great North Road along the west of Auckland. And the current bridge was built in 1947, and it became, when they did the realignment of the existing road, that the bridge became redundant again. So it was used as an access for adjacent car park from 70s to early 2000. In 2005, the bridge became significantly deteriorated because of the floods undermining the foundation of the arches and erosion, corrosion in the rebars, and slope instability of the abutments. So it was a significant safety concerns, and council had to close the bridge. Which was very inconvenient for pedestrians using the car park from the road. And when they looked at the replacement bridge to maintain the existing access, it became something like 2.5 million, which wasn't it wasn't a good business case. So in 2007, it was decided that they could repair the bridge and make it as a part of the heritage trail for pedestrians and cyclists. And that's when we got involved. And it, compared to the full replacement cost, it only cost 420,000 to repair and retain the structure. So just to give an idea, £1 is something like 2 New Zealand dollars. So that's the cost to repair this bridge, to keep it and use it as a part of the heritage trail for pedestrians and cyclists. I'm not sure whether you could read the text here, but I just want to point to the repairs and strengthening, underpinning took place to repair and retain the structure. So the stream was flowing in a way that it has significantly eroded the foundation at the left-hand side, so that we had to do some sheet piling and anchors, rock anchors, to stabilize the foundation. And there is quite a lot of erosion behind the backfall, both abutments. So they had to be sheet piled and filled with flowable mass concrete to stabilize the ends of the arches. And quite a lot of vegetation and slope stability work took place, including drainage, new drainage, to make sure it had proper drainage behind the retaining walls. Addition to repairs to the concrete spalling and cracking, and then new surfacing to maintain the access both sides. Unfortunately, I don't have the photos taken before the repairs were done, but I can show you the photos after the repairs. But it's very difficult to picture how it was before the repairs were done, because it was such a bad condition. And without that, it's difficult to imagine, but still, this is what we have. So this is the left-hand side of the bridge is where the car park, and it provides the access to get to the road, the intersection. And the bridge spans about 15 meters. And then in the right-hand side photo, you would see a short land span to get to the road. And before the repairs done, it had a double T because of the erosion of the soil at this side of the abutment. They had put some temporary double T beams to span that erosion of soil. So the major work is stabilizing the slopes, underpinning the foundations and repairs, and putting a new handrail to comply with the cyclist handrail heights, and strengthening the parapets as well. So this is the car park viewed from the road, and this used to be the double T, and this is only 3 meter wide, which complies with the codes for the cyclist width. And the bridge, original bridge, is something about 5 meters width. So that's the finished bridge. And it provided the access to have that heritage trail going around the stream the bridge crosses. It's a stream runs across the western Auckland. And that's the plaque from the original bridge, which was kept in the second replacement bridge as well. You could see that's the name. And then this is a new plate put on when they opened the bridge in 2007, 2008. So that showed the interesting example for repurposing a bridge when it quite became a redundant structure because of realignment, and the purpose of the use has changed. Now we're going to look at another example of a road bridge over a very busy motorway slightly north of Auckland CBD, which is called Esmond Road Underpass. This is the aerial view of Esmond Road Intergrade. So that's the northern motorway, and that's north and south. This side is the CBD, and this is the Esmond estuary. And this is the connection to a suburb called Takapuna. And the purpose of this project is to improve the public transport of northern side of Auckland with the CBD, and building a bus station in this location and giving a better access to buses coming through motorway and exiting and then going again back onto the motorway, and to better connection between east and west, and improved access to the vehicles as well. So that's the main purpose of this upgrade works, and it's a part of a wider busway project for north of Auckland. So this bridge was built when the original motorway was built in 1960s. So the code has changed since it was built. And then because of the realignment of the roads, we had to build a new bridge adjacent to the existing bridge, and the existing bridge had to be modified significantly to suit the new alignment. So the upgrade works at this intergrade included the modification and strengthening to the existing bridge and a new motorway bridge. I think we can see the piers for the new bridge across the motorway, and this is the existing bridge undergoing the modifications and strengthening. And there is also a new loop for the on-ramp to get onto the motorway as well. So part of the upgrade, the existing Esmond Bridge needed to be raised about half a meter. Not a constant raise, but it's a vertical curve, improved vertical curve, making the bridge go from 0 to 5 meter increase. And also on the western abutment, it has to be widened about 1.5 meters to suit the horizontal alignment. So it had both vertical and horizontal shapes of the bridge. As I said, the bridge was built in 1950s when the original motorway was built, and the time the design loads were H20 S1644, a Ashto design. The current loads are about, the original design load is something like 20-25% less than the current demands. So there itself lies the the significant strengthening or upgrade required. And as you have seen, it's a 3-cell reinforced concrete bridge. The depth of the girders are about 1.1 meters, and each pier is supported on two columns on pile cabs and a group of 6 400 millimeter diameter cast in situ concrete piles. So I just go back and show you. So this shows how we have, this is the dotted line shows the original deck, and this had to be raised up to 1.5 meters. And to reduce the dead load on the existing bridge, we come up with a solution of using polystyrene lightweight blocks and then casting the new deck on top of that with some rebars epoxied into the existing web girders and the existing deck. And I'll show you a better view of that shortly. So the structural assessment or analysis we have done showed that the external web girders, especially close to the piers, was only sufficient to carry about 70% of the shear demand due to the current traffic loads. So it needs to be strengthened to meet the current demands. And substructure assessment pointed to us the pier caps were inadequate for both flexure and shear demands, and the columns were inadequate for the current seismic requirements, and the pile caps also required additional flexural steel for the dead and live load combination. So significant intervention required here to upgrade this bridge for both modifications of the alignment and also to meet the current demands. The photo shows how we have done the new decks. And so these are the polystyrene blocks and the reinforcements, the new deck reinforcement shown in the right-hand side photo. Something to remember is all these work had to happen during a live traffic situation. So we had to build the new bridge first so that we could divert the traffic coming onto the motorway and coming out of the motorway before we could close this bridge to do all these modifications, which is, I mean, the interruption is quite significant, and the temporary traffic management is really, really critical so that we don't bring the traffic to a standstill and make a major headache for the city travelers. We thought about strengthening the webs to improve its shear strength in different ways. And at that time, it was well established the carbon fiber composite polymers were better option because of their lightweight nature and easy to install and less disruption. So this was the first bridge to be trialed on a major structure in New Zealand at the time. And as you could see, they had to cut holes because the depth of the girders are not enough to come through a manhole from the bottom. So they had to cut from the top. And every time you interfere with a bridge like that, there is significant work need to happen. Analysis had to happen to make sure the dead loads can be taken without significant distress to the existing structure. So we come up with a way of putting the carbon fiber wraps internally and externally, and that's provided sufficient additional shear strength for the web girders. And to strengthen the pier caps, we post-tension them by building new concrete leaves and applying the post-tensioning, so improve the flexural and shear demands. And that's the plan view, and this shows the new concrete blocks externally, and the darker color, gray color, is the fiber wraps for the external web girders. To improve the seismic resistance of the columns and to give more ductility in a seismic load situation, we have provided, again, carbon fiber wraps at the top and bottom of 2 layers to improve its ductility. And to increase the capacity of the pile caps, we come up with a overlay and epoxying the reinforcement like this, and it's a very time-consuming construction method. And the reason for choosing this was there wasn't enough space in the median. These columns are in the median, that you could bring big machinery or equipments for post-tensioning. But this was chosen, but on hindsight, maybe post-tensioning could have been a much easier and elegant solution. But you couldn't have closed any of the traffic lanes, especially in the weekdays. Even in the weekends, we couldn't close any of the traffic lanes. So it's a significant constraints in terms of how you could do the strengthening for existing structures when they are in a busy roads, especially on a motorway, which is a critical transport corridor. I mentioned a few construction challenges, but I listed these because I know the time here is well past midnight, and my mind would be a bit, out. So I think one of the key challenges for us was restricted access and not being able to take heavy machinery to the medians or even near the roadside because of lack of space to position them and do the strengthening and modifications. So the focus was to provide the strengthening works, or anything we modify had to be done to fit within the space, and also without making the traffic to stop or anything like that. And we can't take any chance. We need to have contingency plans if that didn't work. So this is one of the main issue for coming up with solutions. I'll show you the third case, which is a existing, I'll take 1 minute to show this. I don't think I need too much time here. This was published in the Structural Engineer magazine in 2017. So anyone interested could take a look. And this also had similar issues in terms of operational requirements, not being able to disrupt the rail operations, and coming up with solution that can fit within the constraints. I think my final words are that any work we do on the existing structures is tricky. And in my experience, the main issue seems always the interruption and how it could be managed carefully. And quite a lot of consultation goes in this situation to make sure everyone's fully informed and stakeholders are taken care of. And often, especially with Makatoti Viaduct, we didn't go through in detail, had significant access restrictions. The challenges often bring give us the opportunity to innovate, and outside the box thinking is critical, and it's often a joyful experience. And it's important to always anticipate the unexpected, because anything can go wrong, and it needs our immediate attention. I think it's reuse, life extension of existing structures are now more important than ever before. So it's important that we share our lessons for better engineering the future. Thank you.